If you ever watch the rocket launch, it never goes straight up, but instead tends to angle itself. But why? More than 400 years ago, Johannes Kepler suggested that orbits of planets around the Sun had elliptical shapes. The shape of a Keplerian orbit could also be any of the conic sections depending on the eccentricity, a measure of how circular the conic is. A circle has an eccentricity of 0, and as the eccentricity increases, the shape deviates to an ellipse, parabola, or a hyperbola. The semi-major axis is closely related to the eccentricity and is half the distance between the orbit's highest point, the apopsis, and its lowest point, the periapsis. Together, these two measurements make up the exact shape of an orbit. Half a century later, Newton's laws help explain why planets orbited in the way they did. You see, an object moving in orbit has instantaneous velocity tangent to its path. This is because the object wants to resist any change in its motion and wants to keep going in the direction that it's already headed to. This is called inertia, or a tendency to remain unchanged unless there is a force acting upon the object. To stay in orbit, the object must have a center-seeking force that constantly changes the direction of its velocity. In our case, this force is gravity. If you remove the source of gravity, the object orbiting the source would keep moving in a straight line because of, you guessed it, inertia. There are two really important laws that govern orbits: conservation of angular momentum and conservation of energy. These laws are really handy because they make up a rather intimidating looking equation called the vis-viva equation. But don't worry, it just tells us that if we know a spacecraft's velocity and position, we can then solve for its semi-major axis and eccentricity to find the exact trajectory that it's going to take. Increasing the velocity in the direction of motion causes the semi-major axis to grow until the spacecraft reaches escape velocity and can no longer remain in a closed orbit. So, a change in velocity, or delta v, results in the orbit's shape to change. Delta v is a particularly useful number because it helps us determine the amount of fuel to use when doing orbital maneuvers such as transferring between orbits. For example, to transfer from a lower circular orbit into a higher one, we first apply a delta v to get to an elliptical orbit. When we reach the apopsis, we fire our thrusters again to get to the velocity required to maintain the circular orbit. The total amount of delta v during this maneuver is our delta v budget, which we need to account for in order to avoid running out of fuel. From going to the moon to landing rovers on the Mars, orbital mechanics have carried us a long way by allowing us humans to achieve great feats and explore our universe further. Thanks for watching.